Welcome everyone to section number 3. This is the fundamental theorem of calculus. And as I mentioned in section number 2, right, we want an easier way to calculate out these definite integrals. These are a long process if you use, the limit as n goes to infinity with the sigma, all that stuff, right? So we want a faster way, and that's going to actually be part 2 of the fundamental theorem of calculus. We're going to get a faster way to evaluate out these definite integrals. But we have to go through this part 1 because part 2 kind of relies on part 1. So that's the objective here, is really we're going to go over the first part of the fundamental theorem of calculus. I'm going to give you an idea of why it's probably true. So the idea of the proof here, not the formal proof, but it'll get us thinking in the right direction. And then finally, we will actually apply this first part of the fundamental theorem of calculus to a few problems. And these are problems that you'll see on your homework. They can show up on quizzes and exams, right? So we'll do a few problems related to this first part. Okay. The first thing I want to tell you about, before I say what the fundamental theorem of calculus is, this first part of the fundamental theorem of calculus, I need to define for you a new type of function, and I want to get a little practice playing with these types of functions here. And so the setup is we have some rate of change function, right? Some r of t, and this is in liters per minute, where t is in minutes, and we are defining this new function w of x, right, which is the integral, the definite integral from 0 to x of this rate of change function, right? How much this pump is delivering at any particular time. So we're adding up and we're getting total change from 0 to x. And so the question is, what does this represent? And I kind of spoiled the surprise already, right? This is the total change in water. So assuming that this pump is, pumping it maybe into a bucket or some sort of reservoir. So it's the total change in water from t equals 0 to t equals x. Remember, these are in minutes. So from 0 minutes to x minutes, whatever that happens to be. But now we're making this a variable where we can stop at different points. So maybe you want the total amount of water from 0 to 1 minute, or 0 to 5 minutes, or 0 to whatever minutes, right? So this is the total change in water from 0 to x minutes. All right, so let's go ahead and use this to evaluate out w of 1, for instance. So w of 1, that is everywhere we see an x, I'm going to plug a 1. So I'm going to have 0 to 1 of r of t dt. Remember, this is just the x's. We don't actually replace the t's, just the x's. So again, w of 1, we replace the x's, so 0 to 1. That's the only x right there. So 0 to 1, again, this is the definite integral. And so we know that this is going to be the net area under our function, so I can go ahead, let's see, I suspect this is 1, 2, 3, 4, 5, 6, good. And so I want this area right here from 0 to 1. That's what the definite integral represents. So I see, for instance, right here, that's definitely 1. Right, length times width of that rectangle. And then let's go ahead and do this little triangle here. That's going to be 1/2 the base, which is 1, times the height, which is, again, 1/2. So this is going to be 1 plus 1/4. That's going to be the same thing as 5/4. So this is saying that maybe 5/4 liters, right, came out of this pump during the first minute, between 0 and 1. So that's the first minute. Now, likewise, we could compute, for instance, w of 3. So this is going to be the integral from 0 to 3 of r of t dt. Again, this is net area, but it's no longer just from 0 to 1, but it's from 0 to 3. So we're going to include all of this stuff right here. Maybe this one I'll actually shade in a different color. So 0 to 3 in this case. And so again, we're going to use this idea that the definite integral is talking about net area. So let's see, all of this, I'm going to do 2, 3, right? So these are all 1 by 1 rectangles. So in total, there's 3 there in rectangles. And I'm going to consider this triangle to just be one big piece. So this is going to be 1/2. And then the overall base of this rectangle is going to be 3 long. And then the height of it is going to be 1.5. So that's going to be the same thing as 3/2. That's the same thing as 1.5. So 3 plus, let's see, 9/4. So that's going to be, let's see, 12/4 plus 9/4. So that's going to be 21 that's a horrible 21. 21 fourths. And again, our units are liters here. Right? This is the total amount that we've pumped out during the first 3 minutes. All right, so now we have a little bit of practice dealing with a function that has an integral in it, right? So kind of one of these endpoints is a variable. So now I want to tell you about its derivative, and that's really what the fundamental theorem of calculus part 1 has to deal with. So, okay, fundamental theorem of calculus part 1. If f is a nice continuous function on some interval a to b, and g of x is defined by, and this is going to have a definite integral in it, and it's going to be from some a value, your starting point, whatever this a is here, to x, some variable, of f of t dt. So it's the integral of some function, the definite integral, and that x, right, that's kind of where we stop integrating, where we stop adding up our area. Then the claim is this g that depends on f, right, with a nice definite integral in it, is differentiable on the interval from a to b, and if you want the derivative, then this is actually equal to f of x. So to some extent, it's saying that the derivative and the integral, they kind of cancel out. And notice that this is not f prime of x, it is just regular old f of x. It's just everywhere you see a t, you plug in an x. So on one hand, this is rather remarkable that the derivative and this definite integral cancel each other out. On the other hand, it's kind of expected, right? Because if we think of r of t, or in this case, I guess, f of t, as some rate of change function, right? And when we integrate, we get total change. And then we ask, from that total change, what is the rate of change, right? What is the instantaneous rate of change? AKA, what is the derivative? Well, the derivative, that rate of change, is just going to be the original function. So remember, you have rate of change function, and then when you integrate, you get total change. And then when you take the derivative, again, that's asking, well, what is the rate of change? What is the instantaneous rate of change? And so maybe it's not surprising that it's actually just the original function. Okay, so the idea of a proof, I would like to give you some notion about why this is true, more than just the intuitive stuff. And so I'd like to start with, right, the definition of the derivative, right? I'd like to calculate out this thing g prime of x, and back a long time ago now, it feels like, in chapter 2, right, we said that this was the limit as some h goes to 0 of the difference quotient, right? So this is going to be g of x plus h minus g of x divided by h. So that is, in this case, we can go ahead and use our definition of g, and g is supposed to be this integral from some starting point a to, and everywhere we see an x, I'm going to plug in an x plus h. So x plus h of f of t dt minus g of x, which is the integral from a to x of f of t dt, all divided by, oops, I did a horrible job here. You're probably screaming at your computer right now. This is supposed to be divided by h. There we go. And now I'd like to be able to simplify this thing in the numerator here, but we really need a better idea of what this is. So I'm going to go ahead and draw a picture here. So here's x, here's some y's, and let's go ahead and draw maybe f of t looks something like this. And we start at maybe a, and we're going to go until x. And so g of x, again, is supposed to be this area under f from a to x, right? That's what the definite integral is. So it's this area right here. And then g of x plus h, right? So we have maybe some value that's really close to x, but maybe it's just a little bit off, right? X plus h, it's off by an h. Something like this. And so g of x plus h is supposed to be the area from a to x plus h. Maybe I'll do this one in purple. Oh no, my purple highlighter is a little bit smaller. This is going to take a second. So something like this. And so again, g of x plus h, that's going to be this one, the purple one, from a to x plus h. And then g of x, that's just from a to x. So that's the green thing that I highlighted over there. And so when you subtract these two away, right, notice that all of this area gets canceled out, right? The purple area minus the green area, all of this goes away. And so what you're left with is just the integral, the area under the curve from x to x plus h. And so this is how we can simplify, and it makes it a lot more obvious when you go ahead and you sketch out the graph, right? Because all that's left is this little sliver of purple right here. And now here's where I'm going to use the idea of the proof and not kind of the formal proof. The idea here is that when h is very, very small, that this is going to be pretty close to the area of a rectangle. The area of a rectangle. And so I'm going to use the limit as h goes to 0. And the area of this rectangle, what is the width of this rectangle? The width is going to be h. All right, so that's going to be h. And then the height of this rectangle, and you can use either the left-hand endpoint or the right-hand endpoint. It won't actually matter in this case. I'll use the right-hand endpoint. So the right-hand endpoint, this is going to be the function's height at x plus h. So the function's height at x plus h. And again, this is where I'm going to do approximately equal to. This is the idea of the proof right here. And then we're going to go ahead and divide that by h. And so we can see now that there's some nice cancellation that happens. And that all that's left over is the limit as h goes to 0 of f of x plus h. And so now that is equal to, well, plug in 0 everywhere you see an h, and that's just f of x. And so therefore the derivative of this g function, this complicated thing with a definite integral in it, right, if you take the derivative of it, that's just equal to f of x. Now if you were to use the left-hand endpoint, similar, right, this would just be f of x. There wouldn't be this plus h, and so you would get the same result. All right, so there is the idea of the proof. Let me go ahead and show you some examples that could show up on homework, on quizzes and exams, right, ways that we can actually apply this. So let's go ahead and figure out the derivative of g of x, right? And this is a function that's defined, let's see, from any old a value, so in this case 1, to x. So in this case, the derivative is just going to be equal to x squared. So that is, right, here is our function. This is our f of t. Our f of t is equal to t squared. And so if you want f of x, well, then you're going to plug in an x everywhere you see a t. So that's why you get x squared. So again, it's just using that first part of the fundamental theorem of calculus, right, that says if you want the derivative of some function that has, an integral from a to a variable x, well, then you just substitute. Everywhere you see a t, you plug in an x, right? It's not the derivative or anything like this. It's just actual f of x. That's a common mistake that I see. People want to do the derivative of, x squared, but you have to resist. All right, find the derivative for this function right here. So now we have the integral from x to 2. And the way that I'm going to solve this problem is I'm going to go ahead and rearrange this before I even take the derivative, and I'm going to make this the integral from 2 to x. Now this is not a free move that we can make, right? You cannot just exchange this. It costs something to switch the order of integration from x to 2 to 2 to x, right? And what it costs us is a negative sign. So this is one of those properties of definite integrals that we learned about in the previous section. So now, if we want to go ahead and take the derivative of this thing, the derivative, well, that negative sign is going to be along for the ride. And again, everywhere I see a t, I'm going to plug in an x. So this is going to be root x squared plus 3. So again, everywhere I see a t, I plug in an x. That's what the first part of the fundamental theorem of calculus says. Let me go ahead and start highlighting these, making them look all nice. There we go. And the final example that I have for you guys is a more complicated one. What happens if you don't have just x's, right? So here I had just regular old x. Here I had just regular old x. In this case, you can see that I have some a value to x cubed. Again, not just regular old x. Well, how does that change? And the claim is we need to use the chain rule here. So this is going to be an application of the chain rule. I'm going to go ahead and let u be equal to x cubed. And then h of u is going to be equal to the integral from -1 to u of sine of 2t squared dt. And now if I wanted the derivative with respect to u, right, now that this is just regular old u, I can go ahead and substitute it in. So this is going to be sine of 2u squared, and that's it. So this again is the derivative with respect to u. If I want the derivative with respect to x, again, I need to use this chain rule, right? So if I want the derivative of h with respect to x, well, this is going to be equal to the derivative of h with respect to u times the derivative of u with respect to x. So again, I want the derivative with respect to x. Well, I have the derivative of h with respect to u. That's this bit right here. So that's sine of 2u squared. And now I need the derivative of u with respect to x. Well, here's u in terms of x. So if I want the derivative of u with respect to x, this is going to be 3x squared. So this is going to be times 3x squared. And now remember, u was something that we created. The original problem didn't have any u's. So I'm going to go ahead and substitute again. Everywhere I see a u, I'm going to put x cubed. So this is going to be sine of 2x cubed squared times 3x squared. So altogether, sine of 2x to the 6th power times 3x squared. That is going to be my final answer. And as you practice and do more and more of these things, you'll get good at just plugging in the x cubed everywhere you see a t, but then you have to remember to multiply by the derivative. So in this case, the derivative is 3x squared. So again, I'm plugging in x cubed everywhere I see a t, and then I multiply by the derivative. You can even think about this on the previous problems. So like for something like this, if you plug in an x everywhere you see a t, and then you multiply it by the derivative, well, the derivative of x is going to be 1. So actually that same rule works for kind of these previous examples. Likewise back here, the derivative of x is just 1. And so that's why kind of it doesn't really matter if you multiply by this 1 or not. You get the same result. But here you have a different derivative, right? The derivative of x cubed is definitely not 1. It's 3x squared. And so that's why we have this final answer. All right, that's it for this first video. The next video, we're going to be talking about the second part of the fundamental theorem of calculus, and that's the part that we're really going to like because it's going to help us evaluate out definite integrals much, much faster. I'll see you then.